You all ready? Okay.
Yes.
So, let's study this function, autocovariance function, in a bit more detail. So, section 1.5. So, we now look at the autocovariance function of a stationary process. So, if xt is stationary, then trivially this holds true. I think we've done this computation already, so let's just do it quickly. We know that this is equal to gamma x of r plus h s plus h for all h. So if I take h is equal to minus s, I go here. And if I take h is equal to minus r, I go here. So I know that if xt is stationary, then this is true. So this is what? Well, that's just a function of one variable. It's a function of the difference, the absolute value of the difference between the time points at which you're looking at your process. So the autocovariance function of a stationary time series can be expressed as a one-parameter function gamma x of h, which is r minus s. This function is sorry, my phone is ringing. I will stop that. No, it's okay. This function is even, and therefore, well, in order to study the covariance function of a stationary process, it is just sufficient to look at the autocovariance function for positive integers as a function of one variable only, and this leads to a notation that we'll be using well, constantly throughout the course. Gamma x of h is just gamma x of h0, where you put the 0 doesn't really matter, and that's the covariance. And I think I try to always order it in this way. So it's xt plus h xt. The h here will have a name. It's called the lag at which you're looking at your process. So basically, you fix t, any t, it doesn't matter, and then you look at a function of only one variable, which is the lag at which you're looking here. Okay. From this autocovariance, we can define the autocorrelation function. I have to be careful with my abbreviations because autocovariance is not ACF. ACF only stands for autocorrelation, although it would be the same initials for autocovariance and autocorrelation. ACF is only reserved for the autocorrelation. And the autocorrelation is what? Well, it's just the correlation. So it's so you must know that the correlation between xt and xs is the covariance of xt and xs divided by the square root of the variance of xt and the square root of the variance of xs. So that's the definition of the correlation of two random variables. And if we translate this for a process, a stationary process, so I forgot the word stationary here. Well, then the autocorrelation function is just a function of one variable, which would be the lag at which you're looking. And it's the covariance of xt plus h divided by the square root of the variance of xt times the variance of xs. But if it's stationary, then both these two here are the same, so it just gives you the variance of x. And the variance of x is nothing but the correlation function, the covariance function at lag 0. So this gives us the definition of the autocorrelation function of a stationary time series. Once again, I think we've said this at least 10 times already, the autocorrelation is a good measure for dependence. If the autocorrelation is not zero, then the variables are dependent. But having a correlation 0 does not imply dependence. It's only implies independence, when the random variables are jointly Gaussian. Okay. So now we have a very useful proposition which gives the elementary properties of the autocovariance. First of all, so be careful with the order in which things are said. If gamma is the autocovariance function of a stationary process, then a number of things happen. First of all, gamma of 0 is always larger than 0. Okay, that's trivial because gamma of 0 is the variance of xt, and the variance of anything is supposed to be non-zero, is supposed to be positive. So the first point is trivial. Secondly, gamma of h is less than gamma of 0 for all h. Well, that's a bit less trivial, but it follows from very, very famous, which you probably all know, and if you don't, you all should know, inequality, which says that when you have the expectation of any multiplication of two random variables x and y, well, that's always less than or equal to the square root of the expectation of the squares So this inequality here is known as Cauchy-Schwarz inequality. It's the basis of well, most of modern mathematics, without joking, because it's an elementary identity which allows to, well, what's important here is the fact that you have something which depends on the joint behavior of x and y, and here you have something which depends only on the marginal behaviors of x and y. And that's a very, very, very useful result. And from here, well, what do we have? We have that by definition, gamma x of h, it's the covariance of xt and xt plus h. Well, by Cauchy-Schwarz, this is less than the... So, I'm not sure if I need to do this in detail. Let's just do it to be sure. So I'm in proposition 1.37. I'm sorry for all of those of you for whom this is obvious, probably all of you. So I have this covariance of xt and xt plus h. That's by definition expectation of xt minus the mean, and then xt plus. Sorry, there's a wasp in my office. I don't particularly like wasps. Okay, that was a very brutal moment. I'm very sorry for you that you had to watch this. A very resistant wasp. It didn't resist the power of Stein's method. Dead wasp now. Wasps are evil. I think humans are evil. I don't think wasps are evil. But yeah, I killed an unbelievable number of wasps during the holidays. You're very welcome, Damiano. It was maybe the most exciting part of my day, so that's good. Where were we? So yeah, so we were here. The covariance is defined like this. Sorry, it's not xt, it's xt plus h. And then I just use Cauchy-Schwarz to say that's what. Well, then this is less or equal than the expectation of the square here. And then that's just what's written here. So it's less than or equal to the product of the variances, and we know that the process is stationary, so this is gamma x of 0, this is gamma x of 0. So whatever happens, if you look at the autocovariance function of a stationary process, well, let's have a look at what kind of drawing can we get. Well, we'll have something like this. So I look at lag 0, lag 1, lag 2, lag 3, lag 4, and so on, h. And what the first result tells us, it tells us that all these covariances are going to be, no, not all positive, of course not. But it tells us that the first covariance, gamma of 0, is positive, it's somewhere, gamma of 0. And then all the other ones, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. All the other ones, all the other ones are going to be somewhere in this band here, somewhere in here. So you could have something like this, and then like this, and like this. But you'll have covariances which would be somewhere in this band of maximum size gamma of 0. Okay, third point, the gamma x of h is gamma x of minus h. Oh, I'm just realizing that there's a small typo. There should be no x here if I've removed x. Well, that's by definition of the covariance of a stationary process, so it is indeed trivial. And then the last point is perhaps the only more or less interesting proof of this first proposition. Do you need to know how to do this? Yes, of course. It's just a computation. It says that, and that's a very important thing, it says that gamma x, so gamma x, well, gamma, or gamma x. I'm not being very consistent here. So there should be no x. It says what? It says that gamma, so gamma is a function from where? Well, it's a function by definition. Gamma is the autocovariance function of a stationary process. So it's a function from n to r, which sends h onto gamma of h. And this function, gamma, is such that whenever I take a1 to an like this, and then I look at gamma of, no, I just have to be careful in the way I'm doing it, gamma of t1 minus t1, so it's going to be gamma of 0, then gamma of t1 just bear with me. It's just a question of writing things out properly. It's not hard at all. I'm just going to translate what's written here in terms of matrices. So I'll have a1 to an, and then line 1 gamma of t1 minus t1, gamma of T1 minus T2 up to gamma of T1 minus Tn, gamma of T2 minus T1, and so on. So I'm building a square matrix of all the differences. And there, that's a bit too much to the right. This is a bit too high. And then I have this. So if I take this product here, so obviously this is the same as, God. Start again, last time. This is the same as this. So here I have 0, 0, 0. On the diagonal I only have zeros. And then off diagonals I have a symmetric matrix, so this guy, I don't need to write him down because it's symmetric. So here I have the same thing as what I have above. Because this thing here is equal to minus this thing here, and so on, and this thing here is equal to minus this thing here. So this is that. Well, what is that? This here is the this here is what? Well, if you work out the computation, it's just the sum over all I j's going from 1 to n of the ai gamma of ti minus tj aj. So I'm just working out the matrix product of a 1 times n vector times an n times n matrix times an n times 1 vector. But it's also, on the other hand, it's also, this thing here is just the variance of a vector, let's call him x, where, so I'll just write it like this. So this is equal to a prime variance of x times a, where, well, a prime, it's my notation for a transpose. It's the transpose of the vector a1, a2, and so on to an. And x is what? Well, x is just the vector xt1, xt2, and xtn. And of course, the variance of this guy, it's what? Well, it's the variance of xt1, which is gamma of 0. Well, then the covariance of xt1, xt2, which is just gamma of t1 minus t2, and so on, like this. So this is obviously, maybe it's not obvious, but if you try it out, you should see that it's actually quite obvious. This matrix here, it's just the variance of this vector here. Oops. And then like this. So that what? Well, so that this sum here aj, it's in fact equal to the variance of a prime x. So this is so that's a vector, that's a line vector, so this gives us a random variable, and this is necessarily a positive or at least a non-zero number. So by this, maybe it's not so straightforward, but if you try it out, you should see that it is actually quite straightforward. Computation, we have the realization that this here is non-zero for all n, for all a1 up to an, and for all t1 to tn. Well, that's quite a remarkable property. That's quite a remarkable property. And that property is called non-negative definite. So a function with this property, a function gamma from n to r with this property is called non-negative definite. And we write it in the sequel, we will write it NND. That is going to come up very, very often. This here. Okay, did you follow my proof of proposition 1.37? Are there any questions? Okay, seems okay. For those of you who are already bored out of their wits, well then maybe you will study this again in a few days or weeks, or you might have questions when you start the exercises. Again, feel free to contact me if you have questions. I will try to answer you. So sorry about those typos. I should remove these X's in a future version of the slides. Quite obviously, we have the same property which holds for the correlation function, the autocorrelation function, with the additional fact that, in fact, rho x of 0 is 1, because rho x of 0 is just the variance divided by the variance, which is by definition 1. Okay. Now, here we saw what happened when you take the autocovariance function of a stationary process. Then this, and this happens. Well, in the other way, you can also show that if I give you any function gamma, which is from z to r, which is even non-negative definite, that's it, so which is even a non-negative definite, then it is the autocovariance function of a stationary time series. So theorem 1.38. Let's call this property star. If I, yeah, I just, this is not, it shouldn't be n, it's z. So here it should be z, of course, because nothing says that the function is defined only on the natural, positive natural numbers. Okay. So theorem 1.38 says what? It says that if gamma from z to r is non-negative definite and even, then there exists a process xt such that gamma of h is in fact gamma x of h. So that means gamma of h is in fact equal to covariance of xt plus h. In fact, I'm forgetting a word. Then there exists a stationary process. So, remarkably, all you need is these two properties. So this is actually quite easy. I mean, even is really easy. It's just gamma of h is gamma of minus h. That's not a very interesting property. So that's not even that's not really a requirement. But this quite intricate condition of being non-negative definite Well, it's basically sufficient and necessary for the function to be a covariance function. And we're not going to go into detail in the proof because the proof requires the use of Kolmogov's theorem. So we're not going to go into the detail of the proof because we didn't prove or even discuss this theorem in detail. But well, how do we do this? Well, what we do to prove this theorem is we assume that gamma is even and non-negative definite, and then we want to construct a process which has this gamma as a covariance. Well, imagine that you have gamma a matrix. So if you have an n by n matrix, which is non-negative definite. So instead of having a function, you have a matrix which is non-negative definite. So this is basically the same. It means just that A prime gamma A is positive for all A in Rn. Well, if you have such a matrix, then gamma is the covariance matrix of what? Well, of X, which would be, let's say, sigma Z for Z multivariate normal in dimension n with mean 0 and covariancy identity, and sigma any matrix such that sigma prime sigma is equal to gamma. So sigma is a square root of gamma. Is that okay for you? So if I give you a square matrix which is non-negative definite, well then gamma, this non-negative definite matrix, can be seen as the covariance matrix of a normal random vector. Maybe I can just show it. There, like this. So the generalization to autocovariance functions and time series is just immediate. Well, what do? You just need to show that well, you define, given your function gamma, you define for any sequence t1 to tn, for any n and for any sequence t1 to n, you define this this matrix here. This matrix is necessary non-negative, definite, so we can find a multivariate normal vector x which has this guy as covariance. And once you're given this, all you need to do is check that the family of random variables so constructed actually makes sense in terms of the time series. And for this you use you just use Kolmogov's extension theorem. So it's not a proof. It's just a comment. Okay. So far, everybody's happy?
Yes.
Good. So So that's why I put a little star here. It's just to indicate that we're not doing this really. We're not really doing a proof. So let's have a look at this kind of argument in practice. So example 1.39, we look at a moving average of order 1 process. Maybe I'll do it in detail, it's better. So example 1.39. So moving average of order 1 process. We take ZT, which would be IID white noise with mean 0 and variance sigma squared. We take theta 1, which is any number in R, and we look at XT, which is the moving average of ZT and its predecessor with coefficients. Why is there a 1 here? There shouldn't be a 1 here. There's no 1. Just take theta in R. And we take ZT, which is the moving average of ZT and its predecessor, with weights 1 theta. Okay, so this is a moving average of order 1 because it's just one time point in the past. Then gamma x of h is what? So, well then first maybe compute the mean. The mean function is obviously m of t is just 0. I hope that's clear for everybody. So that's the first point. Second point, the covariance function of xt and xt plus h. It's what? Well, it's the covariance of zt plus this. Okay, then I just move that around, so that gives me covariance of zt plus h plus theta squared covariance of zt minus 1 plus h plus theta times this. Okay, and then, well, it's exactly the same discussion as what we had given before. This is what? Well, if h is equal to 0, then I have this term and this term which count, but this guy and this guy disappear. So I get simply sigma squared times 1 plus theta squared. And if h is equal to plus or minus 1, well, if h is equal to plus 1, or then this guy disappears, this guy disappears, this guy disappears, but this guy gives me theta. And if h is equal to minus 1, then this guy disappears, but this guy gives me theta times sigma squared, so we're left with sigma squared times theta. And if h is larger or equal to 2, then I get 0. That's okay for everybody? I take that for a yes. Okay, wunderbar. So we have computed the covariance function of a moving average process, and therefore we know for free that this function here is actually, well, even, that's obvious, positive at 0, that's obvious, that gamma h is less than gamma of 0 is also obvious, in fact. And then we have, well, that's far less obvious, this function is also non-negative definite. I don't feel like checking that by hand, But I know that it's true because I know that this guy here is the covariance function, so I know that this guy here is non-negative definite. Now the other way around. So next step. I say gamma 0 if h is equal to 0, gamma 1 if h is equal to 1, and 0 if h is larger or equal to 2. So this is basically the same structure as this function here. At 0 it's something, at 1 it's something else, and otherwise it's 0. At 0 it's something, at 1 it's something else, otherwise it's 0. Now, the question I'm going to try to answer in my next example is what conditions on gamma 0, gamma 1 guarantee that this function here, gamma, is the autocovariance function of, so I should put a little v here, it's a bit dangerous notation, ACVF, of moving average of order 1 process. So what guarantees that this guy here is in fact, so this guy, which I will call star star, is in fact of this form here? Well, it's not hard. It's not hard. All we have to say is that we have to find values of theta squared and sigma squared such that this can be equal to this and this can be equal to this. If we can find that, well, then we'll know that this function here will in fact be the autocovariance function of a process of this form, with theta given by the solution to the problem and sigma squared given by the solution to this problem. So asking the question of under what conditions is this guy of this form is the same as being able to choose sigma squared and theta such that what? Well, such that gamma 0 is sigma squared times 1 plus theta squared, and gamma 1 is sigma squared times theta. Okay, so if we want to be able to solve this, what do we need? Well, we need to simplify this system of equations by, well, we need, one way of doing this is to introduce a new variable, which would be gamma 1 divided by gamma 0, which does not depend on sigma squared, which is then this, like this. So this is always defined, irrespective of the value of theta squared or theta. This is always defined because 1 plus theta squared is strictly positive, and I call this row 1. Now, what do we have? We have that, well, we have that necessarily row 1 plus, well, no, maybe the other way around. So row 1 theta squared plus row 1 minus theta is equal to 0. So if this is true, then necessarily, I just multiply it, this is true. Okay, but then I just maybe reorder this in a more conventional way for a second degree polynomial. It's I need to find, so row 1 is fixed. Row 1 here is given by gamma 1 divided by gamma 0. Gamma 1 and gamma 0 are fixed. So what I need to do is I need to solve for theta. And that's quite easy. Solving this for theta gives me that theta has to be equal to 1 plus or minus square root of 1 minus 4 rho 1 squared divided by twice rho 1. So this is basically just solving a second degree polynomial. And that gives me the roots, if they exist. So what do we see? Well, we see a few things. First of all, so let's call them theta plus and theta minus. First of all, I'll let you check that theta plus multiplied by theta minus is equal to 1. This pretty fact will be actually quite useful later on. It will be a useful property later on. Secondly, what do we see? We see that theta plus or minus are defined in, well, they're real if and only if 1 minus 4 rho 1 squared is positive, which is equivalent to saying that we need rho 1 to be less than or equal to 1/2. Then if in this case, well, then I can take rho 1 is equal to, well, I can take theta, how do I write it? In this case, the process, in this case, the process defined by xt is equal to zt plus theta 1 zt minus 1, and xt, which is equal to zt plus theta, well, it's not theta 1, it's theta plus and theta minus zt minus 1. We have two processes, this one and that one. So xt, let's say xt plus and xt minus, which will have the same covariance. Secondly, not secondly, but thirdly, if if rho 1 is equal to 1/2, then if rho 1 is equal to plus or minus 1/2, then what? Then we only have one solution, which is plus or minus 1. And in this case, we have plus or minus 1, and then we only have one process. And finally, if rho 1 is larger than 1/2, there is no real solution. Sorry, Henry, I hadn't seen your question. Okay, so I guess you answered your own question. So here in the first part, we give ourselves the process and we compute its covariance, but that's not so interesting. There is something we want to do with all this, is that we want to be able to study all these processes in one go, so it will be much easier to start from studying the covariances and then deduce things about the process. And that's what we're doing here. I look at the covariance and then we say things about the process. So, as we will see in the exercises, Another way of doing this is to check whether or not this function here is non-negative definite or not. And what you can see is that if rho 1 is larger than 1/2, then in fact the function is not non-negative definite, and therefore it's not a covariance function. Okay, so far?
Yeah.
Okay, so we'll move on to the last. Oh, maybe you want a break? Do you want a break? Or do we just move on? I'd just like to finish section 1.6 today. Nobody wants a break?
Yes.
Yeah, maybe a quick one.
Yeah, okay. So let's have a break. I stopped the video. We have a, well, let's say a 10-minute break. So we start again at 5:15. See you in 10 minutes.
Sure, see you.